Swayam Prabha. Digital India. Educated India.
Now we want to find out the value of the impedance seen at this distance z from the source. As you can imagine, since voltage and current are varying with z, the impedance will also vary. But what is the mathematical relation for this variance? So to find that out, we first write the equations for Vz, assuming this transmission line is lossless. So say the voltage here. So this, so when we write this expression, in Vz and Iz, here this V plus and V minus represent the magnitude of the forward wave moving in the plus z direction and the wave moving in the minus z direction at z equal to 0. Okay, so in other words, this this V plus and V minus are the values here at the source end. So the value of impedance capital Z of in terms of Z will be equal to V of Z upon I of Z. So again, the assumption here is that this transmission line is lossless. So because it is lossless, we can write this exponent in terms of j beta z. Had this been lossy, then instead of j beta z, it had to be gamma z. Okay, so then if I simplify this, so this is now here, in order to simplify this, let us do a coordinate transformations. Let us go from z to d. Now z is the distance is measured from the source, whereas d is the distance that is measured from the load end. So then z of so d is equal to L minus z, where L is the total length of the L is this one, the total length of the transmission line. So I have this z of d is equal to V plus e raised to minus j beta L minus z plus V minus plus j beta L minus z upon V plus, there will be a z0 here also, because this represents the current. There is a z0 below this. So we have D. Now this, what's the value of this? What is this value? If we again go back to a transmission line, if the value of the forward wave at this point is v plus of z, at this point it is. Similarly, if the value of the backward moving wave is v minus here, at this point it is. So this we can then write as v of L minus, and this as v of L plus, okay, where this v of L plus and v of L minus represent the magnitudes of the forward and backward moving waves at the load end. So then I can write this expression like this. Now, if I simplify this, before simplifying this, I note that the voltage at the load end V of L is equal to V of L plus V of L minus, and the current at the load end is V of L plus minus V of L minus upon Z0. And then I know that V of L upon I of L is equal to ZL, the load impedance, isn't it? So if suppose at this end, so ZL is equal to V of L upon I of L. Now V of L is equal to V of L plus V of L minus, and I of L equal to V of L plus minus V of L minus upon Z0. Okay, so this is how the relationship is, isn't it? So here these two waves, V of L plus and V of L minus, if they add up, they give V of L. If I subtract V of L minus from V of L plus and divide it by Z0, that should give me IL. And then the ratio of V of L upon I of L should be equal to ZL. So coming back to this expression, so then now substituting this value here and this value here, I get okay. Now what I can do here also is I can eliminate V of L plus from these two equations. If I do that, what do I get? I can get if I eliminate V of L minus from these two equations, then I will get, So I can write these two equations. I can write them like this: V of L plus V of L minus equal to V of L, and V of L plus minus V of L minus equal to IL times Z0. And then if I add these two equations, I get 2 V of L plus equal to V of L plus I of L Z0. From this, V of L plus equal to V of L plus I of L Z0 upon 2. And similarly, if I subtract this equation from this, I will get an expression V of L minus is equal to V of L minus I of L Z0 by 2. Okay. So what I have done here is I have obtained the expression for these positive and negative waves in terms of actual circuit parameters, right? So now if I substitute these expressions in this equation, what do I get? So let's rewrite it. Uh, so then this simplifies to the J here. So which can be further simplified as okay, so this is the expression for the impedance at a distance d from the load end for a lossless line. Okay, so if this were not a lossless line, then I would like you to go through the derivations yourself, and in that case the value of z of d would be given like this. So instead of tan, it will be replaced by tan hyperbolic, and instead of beta, j beta, this j would not be here, this beta would be replaced by this gamma, and the denominator would have been so. What do we see from this equation? That it is periodic. So this is, we can also write this in terms as the input impedance of the transmission line. So input impedance at a distance of d from the load end is given by this equation. We note that this is, as the distance increases from the load end, it's not that it goes on monotonically increasing or monotonically decreasing. It's actually a periodic function because of the tan h. D is completely within this tan function. So it is periodic with beta d changing with phi, or in terms of wavelength, it is like for every lambda by 2 distance from load end, the value of z in of d repeats. So here periodic with beta d changing. So every time beta d increases by pi, as you can see from this expression, it will repeat itself. Okay, and so this is true for a lossless line. Okay, so for a lossless line, this is what happens, and for every lambda by 2 distance from the load end, the value of z in d repeats. This is also true for a lossless line. For a lossy line, these two expressions, these two statements are not true. Okay, so that was about the input impedance of a transmission line. So in this chapter, we have covered about transmission lines, the expression for the voltage and current waves, the expression for input impedance, how to find out the values of the real part of the propagation constant for conductive and dielectric losses, what is Wheeler increment rule. So in the next class, we shall further discuss about transmission lines in more detail. Thank you.